All right, I think it's time to start. Milana?
Okay.
Yep.
Hello, everyone. My name is Milana Vuckovic. I work at ECMWF, and I'm guessing most of you know what ECMWF is, but I will explain a little bit. Here with me is my colleague Marta. So Marta and I are working with a team of a few more people on supporting HiDALGO project, and our role is to support use cases in HiDALGO in using ECMWF and Copernicus data. So we help them find the data, understand the data, and in the end, technical part of processing the data and preparing them as input in their applications. So a little bit about ECMWF. ECMWF is both a research institution and operational 24-hour center. So we work to advance science, but also to address the evolving needs of our member and cooperating states. We have 22 member states and 12 cooperating states, and we have around 380 staff from over 30 countries. Besides that we produce weather forecasts, we also operate 2 Copernicus services, which are climate change service and Copernicus atmosphere monitoring service. And we are heavily involved in Copernicus emergency management service, but in this one, we don't run it. We just do parts in it. So what do we do? Our work is has time-critical operational component. We are running our model twice a day, one high-resolution model up to 10 days in the future, and an ensemble of 50 members up to day 15. As our member states are running their regional model on much more frequent production schedule, to support this, we have 2 additional model runs every day with shorter forecast lead time and the limited number of products. We are disseminating around 100 terabytes of data daily to around 200 or more destinations in the world. But we also have a non-time critical component. So we are a research center, and we are continuously working on upgrading and updating our forecast model. We also operate all of this data is then stored in our Mars archive, which is one of the, it's the biggest archive of meteorological data in the world. So so we are producing weather forecast, but which weather forecast? So as some of you know, there is a short range weather forecast, which is a very high resolution weather forecast, which is ran like every 1 or 2 hours on a resolution that can be smaller than 1 kilometer. Then there's a medium range weather forecast, which is on high resolution, which is around 10 kilometers, and it is ran on 6 to 12 hourly production schedule. Then there is extended and long range weather forecast, which predicts statistics of weather for the one coming month or a couple of weeks or months. We ran it once a month or twice a week. And then there are climate predictions. ECMWF does medium and long range weather forecast. We don't do short range weather forecast and climate prediction. Short weather forecast is done by our member states. So our operational forecasting system has these 4 output in these 4 ranges. First, we have high resolution deterministic forecast, which we run twice a day on 9-kilometer resolution and on 137 vertical levels up to 10 days ahead. Then we have ensemble forecast, which has 51 ensemble member. We run it twice a day at a little bit coarser resolution, so 18-kilometer resolution, and it has 91 vertical level. And from next month, both ensemble and high resolution forecast will have 137 levels, so they will match. And this ensemble forecast is run up to 15 days ahead. Then twice a week, we run what we call extended range forecast, which is forecast up to 46 days ahead. That one also has 51 member and 91 vertical levels, but it's again on with a course resolution of 36 kilometers. And then finally, we have seasonal forecast, which we run once a month at the beginning of month, and it is on a bit more coarse resolution, and it's for 7 months ahead. And for this, we don't we calculate, for example, monthly statistics. We don't provide the raw data. So how does this work? First, we collect observations. Then these observations go through data assimilation system. And then when the initial fields are produced, then we run our Earth system model. So it is not just atmospheric model. It has coupled ocean model and land surface model and chemistry. Once the model is done, then production system is started, and then we have the output in these 3 forecasted systems, depending on the day of the week and day of the month. Some days we will only have medium range, some days we will have medium and extended, and some days we will run both, all 3 systems. So what products do we have? So first we have high resolution or deterministic products that are most known and most used products, as they are recognizable and easy to interpret even for a non-meteorologist. These are products on one single level and multiple levels, as we are describing the entire atmosphere, not just one layer. But single layer products are majority, and they are also mostly used. There are over 130 of them. Some are very commonly known, like precipitation products, wind, temperatures, snowfall, cloud products, or precipitation type. But there are other specialized products, such as convection indices, parameters for aviation, for agriculture, and others. Only a small subset of parameters is available on multiple levels, on multiple vertical levels. These include geopotential, temperature, specific and relative humidity, wind, vertical velocity, and some others. These products variables are available on 137 model levels, as well as 25 significant pressure levels. Even though our model is considered one of the best in the world, it should not be used alone. So this high resolution deterministic forecast should not be used alone. And beside our data assimilation system, one thing that makes ECMWF great is our Ensemble forecast system. So why do we do Ensemble forecasting? Since numerical weather prediction models can't produce consistently or precisely correct forecasts, there must be some uncertainty in the result of each forecast. If we could know this value of this uncertainty beforehand, it would be greatly enhance the value of the weather forecast. Because of this, methods have been and continue to be developed to provide the knowledge of the uncertainty of a particular forecast. The ECMWF forecast ensemble is based on the idea that the incorrect forecast is a result from combination of initial analysis errors and model deficiencies. Forecast models can produce incorrect results because of initial conditions uncertainties, like lack of observations, observation errors, errors in data assimilation, and model uncertainties like limited resolution, weaknesses in parameterization of physical processes, or boundary condition uncertainties, like insufficient data of subgrid scale orography and others. So how then we do it? To estimate the effect of possible initial analysis error, an ensemble is formed of 50 perturbed initial states and one unperturbed analysis. The forecast suite is then run using each of the analyses as a starting point, giving a range of forecast results from which may diverge radically or remain broadly similar. The perturbations are constructed so that all perturbed members are equally likely. All perturbations are flow dependent, and they are different from day to day. So consequently, the ensemble of forecasts produces a range of possible scenarios rather than a single predicted value. Addition or subtraction of small perturbation to initial distribution of parameter gives 50 equiprobable ensemble members, each slightly different from the initial unperturbed analysis of the control member. The ensemble members can evolve through the forecast period in slightly different ways, and distribution of the ensemble members gives indication of likelihood of occurrence of different scenarios. In this schematic diagram, compared to the initial conditions, a few ensemble members give this small peak in the ensemble numbers are grouped to give a similar forecast that is cooler, and two forecasts predict relatively much warmer condition, but the majority show the modest warming over initial conditions. Each solution is possible, but the solution associated with the larger peak is more probable. So how do we do this? We have this analysis that is from high resolution for control forecast, and then ensemble of data assimilation is an independent for the data variation system, where the main analysis error sources like observation error, model error, or boundary condition error are represented by perturbing the related quantities. And then set of singular vectors are separately calculated over the northern and southern hemisphere and over the tropics between 30 degrees north and south. These are linearly combined to give 50 different set of global singular values perturbations. Then these 50 sets of EDA perturbations and 50 sets of SV vectors are added together to give 50 sets of global perturbations for the model. And then this is from which model is started. So which ensemble products do we have? We distribute raw ensemble data. So for all parameters, there are 51 value. Then we calculate also ensemble mean and spread for most of the parameters, just to save the resources from our users. Then we also calculate event probabilities for some parameters. So we calculate probabilities that temperature will be, for example, lower than 0 or higher than 30 degrees, or that wind will be greater than 10, 15, or 20 meters per second. Then one of the most complicated products that we calculate is most probable precipitation type. So for each ensemble member, we calculate the precipitation type that will be, and then calculate the most probable of those for each grid point. Another thing that we produce in the Copernicus project is reanalysis. So reanalysis data, reanalysis is what its name says. So reanalyzed observations, because observations can be sparse, observations can be not, the Earth is not covered equally everywhere. We run our data assimilation system. So we produce the analysis, reanalysis for all the grid points on the Earth in continuously in time, well, every 1 hour. It is ERA 5 reanalysis at the moment covers period from 1979 to present, but it is actually extended from 1950. But this data set is at the moment preliminary. But very soon it will be merged, and it will cover the period from 1950 to present. ERA 5 reanalysis is available in Climate Data Store. It is open data set, and anybody can download and use it. Another product that we produce is we run models for Copernicus atmospheric monitoring service data. So we run CAMS reanalysis and forecast data. We run this model daily, and it is similar model as our forecast model. We are also heavily involved in Copernicus Emergency Management Service, which is providing information for emergency response, which includes meteorological hazards or some data for humanitarian disasters and similar things. There are 4 CEMS services which involve flood forecasting and monitoring, which is European and global flood awareness system, European forest fire information system, drought observatory, and Copernicus emergency mapping system. We are involved in the first 2, so flood forecast and fire weather forecast. So this was in short the data that we produce. And now I will show you a quick diagram how we deliver this data. So when the data is produced in our HPC, it goes to something that we call fields database. From there, it goes to our product dissemination system from where it is distributed and pushed to our users. It goes to our archive from which users can download the data by themselves. If they are from our member states or our internal users, they will have the access to our ECMWF infrastructure, and then they can use directly Mars client, which is the most powerful client and API to get the data. Outside of our premises, there is a Python ECMWF web API, which can be used, so that API can be used for public data, or for which anybody can register, or for the data that is under license, for which the users need to contact either ECMWF or Met services. In HiDALGO and one other EU project, which is called Lexis, we are developing a new API to get the data that would specifically target our cloud. So together with EUMETSAT, we have built what we call European Weather Cloud. It is federated cloud from where users can get the EUMETSAT and ECMWF data and process it directly on the cloud. At the moment, it is working as infrastructure, as a service. However, our goal is to have everything as a service. So if the users want just to use the data, they will have, for example, Jupyter Hub, where they can get the data and explore it. If they want to build their own applications, they will have platform as a service or infrastructure as a service. This is a new and ongoing project. So in this context, one of the HiDALGO use cases, it's your urban air pollution pilot. For them, we are exploring moving the processing of the data, of our data, from the HiDALGO infrastructure actually to the cloud. So then in the end, the data that they download is actually much, much smaller than what now they are downloading and then processing. So then here I prepared a list of links where you can find how you can get the data sets and documentation about these data sets. So